Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Appreciate those who've come in the flesh, and those of you out there in Netland, appreciate you watching this, and those of you who are watching it time shifted, also appreciate it. My name is Mike Sinclair. I'm director of the Hardware Devices Group in Microsoft Research, and it gives me great pleasure to host the last couple of days some folks from Universal Laser Inc., based in Arizona, and they make a fabulous tool. We bought one, I guess, about 9 years ago, and as everybody who comes in the lab, I always say, gosh, if I had one of these growing up, my butt would be that wide, I'd be pasty wide, I'd never leave the house. I'd make everything on that thing. So, and it's become pretty much a universal tool in our lab, as a lot of you have witnessed and come in and used the laser cutter. As a matter of fact, again, I like to brag that it gets used more than a screwdriver. Anyway, like I said, we're hosting 3 folks here. I hope you can come by at lectures. They're giving 3 lectures today. Let's see, from the summaries, the lecture today, this morning, will be how lasers work and anatomy of a CO2 laser. The one lecture from 10 to 11 will be laser processing of materials, an overview of the laser system and basic system control, and finally 11 to close to lunch at 12, laser interaction with materials and various applications, and hopefully some tips and techniques for our laser or the laser that you're used to using in your lab. And so with great pleasure, I'd like to introduce Joe Hillman from Universal Laser Inc., and he'll be presenting all the technical stuff.
Thanks, Mike. So thanks again for everyone for coming and for showing up a bit early. The overall intent is to give everyone a better insight into how lasers work and how they function, and to allow you to leverage that insight to make the lasers themselves more useful for you. So, as Mike mentioned, we've got 3 sessions. The first one has 2 sections: how lasers work and anatomy of a CO2 laser. So we're going to cover a bit of the physics that make laser systems possible, both the quantum phenomenon and the optics. And then in anatomy of a CO2 laser, we'll look a little bit into the physical components of the laser systems and what makes them practical. The second session is a little more practical. We'll talk about the laser system itself, and we'll walk through this system in particular, and talk about how the motion system works and how the beam control system works, how we control the pulsing and the power of the pulses. And then the third section at 11 becomes even more practical, and we'll talk about how the beam interacts with various materials of interest and how to optimize those interactions to produce the desired results for your particular application. Then after lunch, Chris and Jim are going to host a hands-on training section where we'll make, this is one of the things we'll make a 3-dimensional cube that each face of the cube demonstrates a different capability of the laser for processing. And I think we're going to do a couple other simple applications. Not simple, I should say. Useful applications that we can do in a fairly short amount of time. So that'll be right after lunch. We got a little bling in the first slide here. So a laser, I'm sure you're familiar with this term. It's an acronym for light amplification by stimulated emission of radiation. So in this first section, we're going to talk about just what stimulated emission is and how that stimulated emission is used to amplify light. So this is going to be kind of a stepwise description. We'll go through the various building blocks that are necessary to make a laser work, and they kind of all add up together to, hopefully, to a final vision of what's happening inside the laser when you hit the start button. So we can use a pretty simple quantum mechanical model to understand the basic phenomenon. The Bohr model of the hydrogen atom is about all we need to understand the basic phenomenon. So this is just a hydrogen atom at ground state with a nucleus and a single electron in the lowest energy level. If we apply energy in any form, light, heat, radio frequency energy, it jumped to the next state all by itself. But that's what happens. Okay, the energy causes the electron to jump from the first energy level to the second energy level and absorbs a certain quantum of energy in doing that. It's not a stable state at equilibrium. It's going to decay back to the ground state, and when it does that, it's got to lose energy, and it loses that energy in the form of a photon of a particular energy and wavelength. Characteristic of the energy gap between the excited state and the ground state. And that's what's called spontaneous emission. And it's happening all the time, all around us at the equilibrium state. And it's spontaneous emission in particular of monochromatic light. So every time this happens for this particular atom, the light that's emitted is going to be of a particular characteristic wavelength. Okay, that's spontaneous emission. We're more interested in stimulated emission, as the acronym indicates, and that's sort of a special case of spontaneous emission that happens when you've got an atom that's already in the excited state. Now, if you add that same quantum of energy to an atom that's already in the excited state, you might think, or at least I would think, if 1 unit of energy brought it from the first level to the second, adding a second unit of energy is going to bring it to the second level to the third level. But that's actually not what happens. And I think it was Bill Gates who predicted in 1914. No, it was Albert Einstein, I guess, who did that. I just wanted to see if anyone was sleeping. So Einstein, somehow or another, postulated that if you hit this excited atom with a unit of energy in the form of a photon, what's actually going to happen is that electron at the excited level in the second band is actually going to decay back to ground state. This first photon is just going to zip right by, and another photon is going to be generated as a result of that energy loss from falling to the ground state from the excited state. And that's what's known as stimulated emission. And the stimulated emission here, one photon essentially creating 2 photons, it's an emission of coherent light. So coherent light, of course, means that these 2 photons have the same frequency, the same wavelength, and the peaks and troughs all line up. So this emitted photon kind of sees this photon coming and just kind of gets running, and then they just take off in step as they pass through. So that's stimulated emission. Stimulated emission requires, of course, the atoms to be in an excited state, but thermodynamics dictate that for any population, you're going to have a larger number of species in a lower energy state than a higher energy state. Boltzmann's principle in particular says the collection of atoms, if it's in equilibrium, the upper level, which is the excited state, will always be smaller than the lower level. So if we want to rely on stimulated emission to give us this laser beam, we've got to get into a different state, a non-equilibrium state. And we do that by pumping in extra, there we go, pumping in extra energy. The extra energy gets us up to a level, a non-equilibrium level, where we've got more atoms at the excited state than we do in the ground state, and that's called population inversion. So that's another requirement for a laser beam to be excited. So we've got our box. Sorry, I probably stepped through that too fast. So this was the box of laser medium containing various atoms that we're trying to excite. So we're adding energy. We're getting into our inverted population where we've got more atoms in the excited state than at the ground state, and that's causing stimulated emission. So we've got one electron hitting an atom that's already in the excited state. We've got stimulated emission, so we've got one a photon creating two photons. Those two are going to create four, et cetera, et cetera. And they're going to keep going until they hit the wall or until they hit something else, and then they're going to recombine and kind of die away. So it's happening over here in a different direction and over here in a different direction. So we're amplifying light in the sense that we're creating more photons, but it's not very useful to us because it's going off in all directions, and we've got to have a containment here to hold in our case, our CO2. So nothing's really escaping. So how do we take advantage of this application and make something useful out of it? And that's done through strategic placement of mirrors. So we place a mirror at the end of each cavity. I just drew these as square blocks, but in reality, the shape of the mirror and the distance between the mirrors are critical toward creating a resonance. So once you've got the mirrors here, you're still having stimulated emission occurring in this direction, but again, it's going to hit the wall and it's just going to become useless, in a sense, stimulated emission. The stimulated emissions that we're interested in are the ones that are going exactly parallel to this resonance cavity. So this one will become 2 and then 4, hit the mirror, bounce back, and become 8, 16, on, and keep amplifying itself. So now we've got light that's amplifying itself, but it's still kind of trapped inside of our enclosure here. So in order to get it out, we need to turn one of these mirrors into what's practically a half-silvered mirror, or we call it a beam extractor. So the photons are traveling back and forth. They'll hit this mirror and be totally reflected. When they hit this mirror, about 80% of them are reflected back, and about 20% are extracted in the form of a laser beam. If anyone has any questions or comments, by the way, yeah, please.
Do you have any way in a gas laser to control the angular spectrum of that generation of stimulated emission? It seems like you'll have, if it was isotropic, you'd have very little of a very small population normal to the mirrors. When the stimulated emission is generated, is it just isotropic, pointing in all directions, and you get a small fraction?
Yeah, when it's generated, it's isotropic. The way we apply energy is through RF electrodes. So we've actually got a plasma inside the laser beam. So it's pretty much isotropic, and the only thing that we've got to control it is the shape of the mirror here. And the shape of the mirror kind of it focuses things, but the initial generation of the photons is isotropic. But yeah, by all means, if you have questions or comments, the whole idea is to make this useful for you, and ultimately to make the lasers more useful. So we want to have plenty of discussion as we go. Okay, so that's the essence of what makes the laser beam work from a physical and optics standpoint. So just in terms of a summary, we need to excite the atoms. We need to excite the atoms and then have actually population inversion so that we can sustain this the stimulated emission that we're going to rely upon to create the amplification of the light, and then strategic placement of the mirrors to get them to the beam extractor and extract the beam in a useful form. The characteristics of the beam, they're monochromatic because they're all reliant upon a certain vibrational frequency of the CO2 atom. The very nature of the stimulated emission is that it's going to create coherent light, and then of course the placement of the mirrors is what gives us the directionality of the beam. Mm-hmm.
In that it's coherent, is the polarization the same for all elements of the beam also?
Yeah, the polarization is the same, and that can lead to well, I was going to say it can lead to problems. You just need to understand that the beam is polarized, which means the mode that's extracted at the end doesn't always give you a perfectly round beam in terms of energy distribution. You can have an oblong beam. So if you're cutting, for example, that can mean that if you cut in one direction, you've got a narrower curve, and then as you cut in the orthogonal direction, you can have a wider curve. One way to account for that is to use a dual laser system. We've got a dual laser system that'll rotate one of the beams orthogonal in terms of polarization to the other. So you've got essentially a round beam, and it really helps those curve problems and keeps the curve the same regardless of the direction that you're cutting.
Well, what causes the polarization phenomenon? It doesn't sound like mirrors, which are pretty much homogeneous over their surface. What causes the polarization?
I believe it's the nature of the stimulated emission. That if the first photon has a particular polarization, the one that it's stimulating is going to have the same polarization.
It has always the same polarization, does it not?
I believe so. Yes. Yeah. I think that's correct. Certainly, the beam has a particular polarization.
You don't have a Brewster window in there or anything that causes polarization or higher reflectivity in one polarization angle than another? They're just flat mirrors, right?
They're not flat mirrors, but they're set up to create the resonance. Yeah, that's. I wish I could give you a sounder answer, but we can certainly. Can you take a note of that question, Jim, Chris?
Sure.
And we'll make sure we give you a more solid answer. We'll have to talk to we've got an R&D group that kind of lives in a secret room that puts the lasers together, but I'll get you a more solid answer to that question. Okay. Any other questions about this first part? So that's kind of a broad brush overview of the physics, but hopefully it gives a fairly sound understanding of basically what's happening, and that understanding maybe will make the systems more useful for you.
So is yours an all-line system, or is it just what's the strongest P6 or P20? I forget what's the strongest line in CO2 lasing. Are you an all-line system?
Yeah, we focus on the 10.6. The 10.6 micron wavelength is the strongest peak. We can focus on that particular wavelength, or we can focus on there's a shoulder peak at 9.3 microns that we can also.
But much less power, right?
In the end, we can we tune the laser to a particular power based on the physical design of the laser, but it's a weaker peak. It's a weaker peak, definitely. The 10.6 is generally used for the very reason that you mentioned. It's a stronger peak. 9.3. We try to evaluate it for various materials. The one material that we've definitely found that 9.3 is valuable for is PET. It just loads into the PET better, and we've seen it give a much better mark on PET, and it cuts much more cleanly. So just kind of an overview. I'm going to focus on the CO2 lasers because it's a very useful type of laser, and it's the one that's here at Microsoft. It's the type that's here at Microsoft. But just as an overview, this electromagnetic spectrum with the visible spectrum in the center. CO2 is as we just talked about. We're using the 10.6 micron wavelength. And we'll talk a little bit more about why that's valuable. We can also make use of 9.3. Another popular type of laser is the neodymium YAG laser at about 1 micron. That's very effective for metals, for cutting and marking metals, because that frequency can load into the metals and interact with them much more efficiently than the CO2 laser. CO2 laser can load into metals, but you need a lot more power. You need to heat it up before it'll be susceptible to that frequency. A less expensive and easier to deal with version of the YAG laser is the fiber laser. Fiber laser is just it's a glass fiber that's doped commonly with yttrium being the lasing medium, and that's where the stimulated emission occurs within that core of the fiber. Three other lasers, I'm sure you'll recognize these. These are all solid-state lasers, aluminum gallium arsenide at 780 nanometers. That's the typical laser that you'd see inside of a CD player. And then at a bit shorter wavelength, indium gallium aluminum phosphide would be the typical laser in a DVD player. Tighter packing density of data due to the shorter wavelength of the laser. And then this is Blu-ray down here, a gallium nitride laser at 405 nanometers. And then state of the art in the semiconductor industry now for patterning 22 nanometer circuits is the argon fluoride excimer laser. Krypton fluoride was the last step in the roadmap at 257 nanometers. So state of the art now is argon fluoride at 193 nanometers. And we could pack this spectrum with different sorts of lasers. I just picked those out because they're kind of interesting and somewhat well known. So why is there such an interest in CO2 lasers? It was invented back in the 60s at Bell Labs, and it's been around for a long time, but it's still one of the most widely used lasers in research and in industry. One of the reasons for its usefulness is it's fairly low cost and high energy conversion efficiency. But it's also got a huge range of applications. It's applicable to it's highly applicable to just about any organic material because the wavelength loads into organic materials very well, and at a fairly low energy you can mark or modify or cut organic materials, polymers, woods, even materials like leather. If you get the power density high enough, you can mark or cut metal. So it's just a very versatile and cost-effective laser. This schematic shows the key elements of the laser. I mentioned before we've got RF electrodes inside of the laser. So those are shown here. We run at 40 megahertz. This sort of cross-hashed line represents the enclosure. Inside the enclosure is a gas mixture, which is primarily nitrogen, actually, despite the fact that we call it a CO2 laser. And we'll talk about the gas mixture in a little bit. This mirror, at least in our design, has a spherical cross-section to help focus those spontaneous emissions back toward the center line. And then an output coupler or beam extractor, which is a partially transparent mirror at this end. And I'll show you real quick here. This is the laser itself. So there's an outside, just an aluminum box that keeps fingers and stuff away from the electricity. And then inside is a sealed, cast and machined aluminum box that is the gas enclosure. We load it with a mixture of gas, particular mixture of gas, nitrogen, CO2, and helium primarily. And that's sealed off. There's a desiccant inside that helps keep things dry. And there's a feed through, of course, to the RF electrodes. So I mentioned the gas mixture. The nitrogen, a typical mixture might have 70 to 80% nitrogen. It's the nitrogen that's actually being excited by the RF. And the reason nitrogen is chosen is because it has a relatively long mean free path. So it's likely that it's going to hit a CO2 before it recombines with another nitrogen and falls back to the ground state. So the nitrogen eventually is going to collide with a CO2 molecule, and it's going to excite that CO2 molecule just by energy transfer from the collision, and it'll excite several rotational and vibrational states, the most predominant of which is the one that's associated with our 10.6 micron emission. It's the CO2, of course, that's responsible for that stimulated emission of the photons once it reaches the inverted population state. So that's why we refer to it as a CO2 laser, even though the gas is mostly nitrogen. It's the CO2 that's responsible for the laser phenomenon. And helium's in there as a transfer gas, because we got to get the CO2 back down to a ground state in order for it to be re-excited, and the helium has a very high specific heat, so it helps with heat transfer out to the walls and out through the heat exchanger.
Question?
Yes?
So, I'm not sure I understand. With all three gases in there, do you get won't you get some lasing of the nitrogen and the helium?
The helium and the nitrogen don't exhibit the spontaneous emission phenomenon.
Why?
That's a very good question.
That's another one to put on the.
That's a very good question. I'm not sure.
I mean, there are helium neon lasers, for example.
There are, yes,
You
indeed.
know, and so. Okay. And what's the definition of a long mean path that was on the previous slide? I'm not sure I understood what that means. It sounds as though what you're saying is that typically a light beam doesn't hit these nitrogen atoms very easily. It hits the CO2 instead. Why?
The RF frequency is going to excite the nitrogen atom. Okay, and then the nitrogen atom is going to have a higher likelihood of hitting a CO2 atom before it hits another nitrogen atom with the right physical characteristics to cause it to recombine. Okay. Any more questions or comments?
Wall plug efficiency factor you realize?
About 20%, 20 to 25% would be typical for a conversion from the plug to the beam.
Any laser.
It is indeed. CO2 is one of the most efficient for energy conversion. All right, that's our first section. So we covered an overview of the CO2 laser itself and the physics that govern it and the basic components for putting it together. So the next session is at 10, and we'll cover the key systems of the key components of the laser system, how we control the motion of the laser beam, and how we control the pulsing and the energy of the laser beam. And then at 11, we'll get a little bit more practical and talk about laser beam interactions with materials and how we create applications out of those interactions. Yes?
So the collimation of the beam coming out, I can see if it's flat against flat, it clearly comes out collimated. But being slightly spherical, I assume it's slightly not collimated. Is that correct, or is it?
It is correct. There's some divergence to the beam over distance. It's not completely collimated. It tends to diverge, and then we refocus it with the final focusing lens just before we hit the material.
What is the smallest spot we can generate on the laser we have?
Smallest spot is about 40 microns, about a thousandth of an inch, with what we call high power density focusing optics, where we actually insert an extra collimator. It serves as a beam expander and a collimator. So we expand the beam out and collimate it so that it can focus down onto a much smaller spot size. Standard optics, without the collimator, we can get down to about 0.003 of an inch, or about 120 microns. The beam as it comes out to the laser is about 0.008 of an inch, and if we run it through the beam expander, it increases it by about 50%, I believe, to about 12 thousandths. And then we can focus it down, in the case where we have the beam expander, to about 1,000th of an inch. There's a trade-off there. Of course, if we focus it down to a very small spot size, that gives us less depth of focus. So with the high power density focusing optics, we can engrave very fine lines and fine detail. And we'll talk a lot more about this in the second session. Fine detail. We can also cut thin materials, but you'd like to take advantage of that to cut thicker materials with a smaller kerf, and you really can't, because we're focusing down to a very small spot, which means the beam's going to converge and then diverge fairly quickly.
And how fast can we pulse this one?
We can pulse it 1,000 times. I'll have to do math in my head, because we go by pulses per inch. So we pulse it a maximum of 1,000 times per inch, and our fastest speed is 70 inches per second. So yeah, 70 kilohertz, right?
And you do that because you can't keep tangential speed constant?
Why pulse instead of continuous, I think, is the way I would ask the question.
If you had continuous movement and constant tangential speed, then you wouldn't need to pulse it, right? For the maximum power.
Oh, to get maximum power?
I mean, why do you pulse it?
We pulse it so we can control the power, get higher or lower powers. And the tie-in with speed is that if we want to go around a corner, if you keep the speed at 100% and try to turn the corner, you're just going to shock the system, and instead of hitting it and turning a corner, it's going to hit it, and it's going to ring back and forth and stop. So we actually slow the beam down. We're going at 70 inches per second. We slow it down, turn around the corner, and speed it back up again. So as we're doing that, if we want to keep the number of pulses per inch constant, we have to change the number of pulses per unit time.
So I gather then the game that's going on then is you're keeping, the pulses per inch constant, right, as you do that. But is there a thermal effect that, as you slow down, they start to bunch up, or, you don't have as much time to remove the heat from that area?
Yeah, that's what we're trying to overcome. So we slow down the number of pulses. We slow down the frequency, basically, but we're trying to keep the number of pulses per inch constant. So the carriage is traveling slower, but we're slowing down the pulsing of the laser, so the number of pulses per unit length across the material remains the same.
But it sounds like that should also vary, so you should vary with material thickness and with the material, how well it removes heat, right?
Yeah, the thermal conductivity of the material matters a lot. Some materials, as I'm sure you know, respond much better to a high pulse density. They need that heat affected zone in order for the laser to interact with the material and do the work. But others just melt or char if you put too much of an energy density into them. So that's really a critical factor, is managing that energy density going into the material. And it's quite a chore for the software engineers to try to keep the energy density that the material sees constant, regardless of this changing speed around corners and around curves, or if we're doing a raster pattern where we're going back and forth and we've got substantial overlap of one trace with respect to the other. We try to keep, we've got manual system controls that allow the user to interface with all this capability, but in general we try to keep that level of complexity inside the software so that the user can basically just push a speed button and and the software figures out how to run the laser most efficiently.
So are you actually pulsing the RF to the laser, or are you actually using a shutter to create the pulses? I mean, how are you creating the pulses?
Pulsing the RF to the laser,
Okay.
which creates pulses very efficiently. There are other ways to do it, like with a shutter, with an optical shutter, or with a Q switch, which gives you a much higher peak power. But the way we do it in our lasers is by pulsing the on signal to the RF generator.
So I've often heard that different manufacturers claim their tubes have different lifespans. So what are the factors that drive the lifespan of the tube?
The major factor is the lifetime of the gas. In other words, how well the gas is sealed inside of the laser itself. So the aluminum power plate type lasers tend to have a much better lifetime than the glass tube type lasers.
Because the gas is just escaping through that or something?
Yeah.
But the non-recombination of CO that's made, because you do make CO radicals, right? That
Right.
necessarily get reconstituted as CO2. And does that claim the life of a laser also?
I would think it would come to an equilibrium state. I don't think that would affect the life, as long as the gas that remains stays at an equilibrium state.
So to refurbish them, do you just exchange the gas, or you said?
Yeah, we do. I mean, there's a series of electrical and mechanical tests that we do, but basically that's it. We pump out the old gas, we run dry nitrogen through it to remove any water vapor, and then we pump in a new gas mixture. We do a test of the mixture that's in there after it's filled with a residual gas analyzer, and then we test the output beam. We usually test the stability of the power and the mode of the laser, both in energy space and in time space as a quality control test. But the basic refurbishment is changing the gas.
The electrodes there's nothing happening to the electrodes. There's no aging process there.
Nothing substantial. When we refurbish them, we don't take them apart. If they behave properly electrically, then that's an indication that there's nothing wrong. There's no aging process. They could be damaged mechanically, I'm sure. They're held off from the ground surfaces by some small alumina bearings. We just use bearings. All they're used for is spacers, but you can buy some fairly inexpensive alumina bearings that can act as standoffs. So those could fracture due to impact, but if it tests out electrically, that indicates that the spacing between the electrodes is held.
What's the typical operating temperature of the tube?
Trying to remember because I believe it is 40 degrees C. Does that sound right? I did some, I'm sure it's in our manual, I did some experiments about 6 months ago where we're looking at the effect of beam stability versus temperature, and I think we were at 40 degrees C. Basically regardless of the output power of the laser. If it's a higher output power, you're going to have more heat discharge, but then again we put bigger heat dissipation fins and fans on the heat sink. That's the word I was looking for. We put bigger heat sinks and fans on the bigger lasers to keep them at temperature.
So I have noticed in playing with the laser that over time it seems like the power of the laser is changing, particularly on really long cuts that might take an hour or two. It really seems like the depth of cut is changing quite a bit. So what causes that? Is that just the system malfunctioning, the lens getting dirty, or is the laser somehow warming up, that it's changing its power? Or
It does warm up over time, and temperature does have an effect on the power. It shouldn't, on that time scale though. It usually peaks when you first turn it on, and then as it heats up, the power is going to drop down. It usually drops between 5 and 10% over about 15 minutes, and then it should stabilize after 15 minutes if it's behaving correctly.
So do you, when you turn on laser, is it running it so that it can get to that stabilization? Or, because we generally leave it off and then turn it on, when we're about to use it. Should we let it sit for 15 minutes to stabilize? Or should it be actively cutting for 15 minutes? Or
if you need to have it completely stabilized, it should be actively cutting for 15 minutes. It doesn't have to be cutting at high power, but if you need to have the best stability, you should actually run it for 15 minutes.
So it would make sense to have like a piece of sacrificial material that is just randomly cutting over here or something.
Yeah, I would say for 90% of applications, you don't need that good a control. But if you do, at least for 90% of the applications that I run into, so I wouldn't say it's necessary to do it as a standard practice, but if you're trying to cut, for example, a vector cut to a particular depth through a material and you want that depth to be stable, then that would be a good idea. If you're cutting through a material, you generally want to overpower it a little bit anyway to break through cleanly, so it would be overkill to warm the laser up. Yeah,
so you actually pulse width modulate the individual pulses to get the RMS power level, right? And that's where you change the power level on the settings. And does that I assume changes the width of the pulses?
It changes the width of the pulses. Now we call it a power setting. It's really a duty cycle setting. We're changing the amount of time that the laser's on. A 75 watt laser is always going to have a stable output at 75 watts. What we call 50% power means it's on for 50% of the time and off for 50% of the time.
So can you not sample the output beam and put a modulation on top of that to keep the power constant?
Yeah, definitely. Definitely.
You can or do?
We don't.
Okay.
It can be done. It adds cost. So that's one of the factors. But that can definitely be done.
So let me make sure I understood what you just said, and that's it. You're going to have 1,000 flashes per inch, but depending on the power setting, the duration of each individual flash is controlled by the power setting. Is that correct?
Right.
Essentially. So the number of flashes is always constant, 1,000 per inch.
Class B.
No, you can change that as well.
But it's not based on power settings.
It's based on pulses. It's a pulses per inch.
Yeah, it's dots per inch. Yeah, right.
Yeah, dots per inch. So you can change how many times it turns on every inch, and how long it stays on.
Right.
After each turn on, independently.
Following up for his question, you need 15 minutes of cutting time to warm the laser up, so to speak, in 10% of the cuts that we would do. Is that if he just got done cutting something for an hour, and then 5 minutes after he's done, I get on, and do I still need that 15 minutes warm up time?
No.
So
that would just be warming up from room temperature.
Okay.
If you look at the power output, which is what our sort of QC test for every laser, they put it on a bench, turn it on. The power rises to about 10% over the rated power, 5 to 10% over the rated power over the first maybe 2 minutes, and then it decays down to the rated power over the next 12 or 13 minutes.
So it sounds like what I've been doing is totally wrong, because usually what I'll do is I'll put in a piece of material, I'll check the numbers, I'll fudge them until it's just cutting through, and then when I run a long piece, I'll often find at the end that it isn't cutting through anymore.
Yeah.
Okay,
I
so
would turn the power up a little bit more.
yeah, that's what I'm wondering. So it'd be good to have some guidelines as to how much more.
Okay. We can, one thing we should probably do is make sure that you've got the power curves for the lasers that you've got in-house.
Yeah.
Because we would have those on record, and that'll tell you exactly how much it's decaying over time, and what that timeline is. Mm-hmm.
Where are the optics, the coupling optics made of? Or just glass? Or?
It is, no, it's not glass.
zinc selenide? The elements?
No, I don't think so.
But do those get hot too? Do they get hot? Is that what
Yeah, they do. The mirrors are silicon. For some reason, the lenses. Is it zinc selenide? It is? Okay. Sorry. Yeah, it is zinc selenide. Lenses are zinc selenide. Mirrors are silicon, and they do get hot, and that causes.
Real hot if you cause something to deposit on, and they'll crack.
Yeah.
No.
Yeah, with the lenses in particular, you got to make sure that they stay clean, and keeping that airflow through the cone is one of the chief ways to do that. And just whenever you're going to cut something, unscrew the 2 screws and take a look at it and make sure it doesn't look cloudy, and clean it if it does. A more subtle effect is when the mirrors and other components of the system start getting hot, and then pieces of the laser itself start to expand thermally, and that essentially causes the laser to scan through some of the shoulder frequencies and pop just off 10.6, and you can get higher power versus lower power modes with just slight distortions of the laser, physical distortions of the components of the laser.
If you see something, some cloudiness, what do you clean with? Alcohol? Or?
Lens cleaner, which is usually an alcohol. Isopropyl alcohol works fine. You use lens paper, so you don't scratch it.
And the first surface mirrors, you have to be even more tender with, right?
Mm-hmm. Yeah, the ones that are inside the system, of course, are sealed. This is the laser itself. I'll just kind of point here. So there's 2 inside the laser itself that are sealed. And then there's this runs back and forth. And this goes back and forth. That's how we get our motion. So the one here and the one here, of course, are inside the cutting area. So those are the ones you have to be the most careful of, because when you're cutting, you're essentially burning through the material, and that generates smoke, which is going to deposit on any cool surface and condense out. But just keeping it clean is really the key to consistent performance. Yes?
I have noticed an uneven power distribution. I'll be cutting something that is occupies the entire bed of the cutter, and over towards the lower left corner, it seems like there seems to be a diminished power. I don't think it's a time thing. It seems like it's in relation to the center of the bed, basically. And I haven't noticed it anywhere but towards the lower left corner. Is that
that's probably due to alignment of the beam. Probably. So when this is where the beam is extracted from the laser. So if you're lower left corner back here.
Correct.
Okay. Usually, let me hit the usual problem first. When you're way over here, that's where the beam's traveling the furthest, right? It's got to travel this distance, when it's got to travel this distance. So if there's an alignment problem with the mirrors, sometimes you don't end up coming right through the center of the final focusing optics. Now that problem can exist in different places. It can exist here, or it can exist there, or it can even exist at the very beginning. Usually the problem is a beam alignment problem. And there's a beam alignment procedure that we can go through if you're not familiar with it. It essentially amounts to putting something over this hole, like just a piece of tape, and firing the beam and making sure that you're burning right through the center of it. And then there's adjustments to each of the mirrors to make sure that you're, so you can adjust that so you're right in the center. But that's generally the problem.
The only other problem I've seen there is that the table isn't perfectly flat for some reason. Maybe the cutting table isn't sitting flat in the center. Then you might have it out of focus, and that won't happen.
That could be an installation issue. could get whacked and get out of
It
level?
could get back. Yeah, the easiest way, just check with a focusing tool and all four corners.
No horse playing the left.
Well, you want to take a short break?
Yeah, let's
Okay.
go to the next one.
Take a little break and.
Coffee and drinks are out there.
Yeah, actually, the groups are here.